Hi, welcome to another Teardown. This one's been anticipated on the forum ever since somebody on the forum actually found out about this puppy before it was released. It's the new Agilent Keysight. Look at this ridiculous looking logo. Isn't that the most boring, pathetic looking bland black logo you've ever seen? Unbelievable. Anyway, this new 34470A 7.5 digit multimeter Agilent Keysight have never made actually a 7.5 digit multimeter before. Apparently they've done the 6.5 digit ones with the new 34461A series we've seen before. They've also done, of course, their famous 8.5 digit transfer standard meter, but this is their first entry to the 7.5 digit market. And of course they're using the same model and form factor as the 34461A. It's their Truevolt series. So they're now actually got two models. There's also the 34465A, which is around about $1,400, and it's a 6.5 digit one. It's got some improvements over the 34461A, which all these bloody model numbers, so confusing. Anyway, we've looked at the 34461A before. There's the new 34465A, which is a bit more expensive, and there's a couple of people on the forum actually who've traded in already their almost brand new 34461A for the 65A. So, because it offers some nice advantages for not much extra cost. Anyway, this one is $2,900 or thereabouts. That's the street price that I found, and it's for the 7.5 digit model. So, and it's got some nice new features on it, which I'm really interested in seeing, particularly the current ranges. It's still only got the 3 amp jack on here, but it actually has a 1 microamp full-scale current range. Wow. So I can't wait to do a review on this and have a play around with that. But anyway, that's not what we're doing today. We're going to take a look inside, because a lot of people have been asking what is the voltage reference used inside this thing, because it's a lot better than the 34461A and also the 65A, which still uses the LM399. And we suspect this one doesn't use the LM399 because its specs are probably not good enough. Or the specs are too good to be using that reference, which is, it's like they quote about 16 ppm basic DC volts accuracy or something for this thing. Pretty kick-ass meter, and it's a reasonable value for a 7.5 digit meter at the almost $3,000 price point. Yeah, it's not sort of hobbyist or your basic lab pricing, but hey, when you're paying for 7.5 digit meter, you're paying for the huge performance in the thing. And as you can see, practically identical to the 34461A here. So nothing is really changed, except this one, it does have auto cal. You can go shift auto cal like that. That one, the 61A, doesn't have that. But apart from that, everything looks identical. And absolutely no difference on the back either. If I swap those over, you wouldn't have even known which one's which. So, you know what we say here on the EEVblog, don't turn it on, take it apart. And here we go. Of course, we expect it to look near identical to the previous one, the 34461A. Ta-da! We're in like Flynn. Look at that. Isn't that really neat and tidy? I've mentioned this before with the 34461A teardown, but that is just, yeah, that is just gorgeous construction, well thought out, and nice tidy wiring on their mains transformer there. Got a good old-fashioned linear one there. I like that, although there is a switch mode down in there. We'll get into that, but yeah, that's all the magic is going to happen under, that, I think I might see the magic. Under this shield here, there's some sort of plastic holder. That's got to be the reference. That's got to be it. Absolutely. So, yeah, let me try and take that off, and we'll be in like Flynn, because everything looks pretty much the same as what we got last time, so I probably won't go through all the details. It looks near identical. Now, nice huge HRC fuses over here, absolutely massive there, fairly easily user replaceable. There's only 3 screws to get this case cover off. There is a bit of a trap for young players. These little clips here, you've got to sort of like pull this out a bit before the case will actually pull off, so it's a bit annoying and not obvious at first. Anyway, Seba brand fuses in there, so have spared no expense. We've got our tellurium, they're exactly the same custom molded tellurium copper contacts, low thermal EMF contacts, front and rear, of course, and the big physical clunking switch in here going into this ganged switch down here, which then, well, it's not ganged switch, it's a just a multi-way switch down in there, which switches between the front and rear panel terminals, and everything looks very similar, if memory serves me correctly. Of course, I'll have all the high-res photos available on EEVblog.com, and you'll be able to compare it with the 34461A. Got ourselves a nice spark gap over there, nice isolation slots. Anyway, that is just gorgeous. And I also loved how, my pointer's gone, I loved how they have these little hooks in here. The board just slides into these hooks and then just slides forward and out of the case. It is very, very nice, but that's what everyone wants to see. That's the money shot under there. Let's get to it. Oh, check this out. This is really interesting. This is more than what I expected in this thing. I expected like just a Lineartech LTC 1000 voltage reference, and we may still have that, but look at this like module here. This is like, you can bet, I don't know what's under here, but you can bet your bottom dollar this is the reference. They don't go to this amount of trouble to make a second daughter board like this with some custom plastic carrier like this and a header on top, and just for, you know, some miscellaneous thing, this is definitely the voltage reference, which they've no doubt, the reason they've put on a second board is so that they can maybe thermally age these things separately and test and characterize each individual one as a separate process to building the multimeter itself. And this is really interesting. They've got an 8-pin header on there, so that's obviously how they plug into their production test jig for these things. So whether or not that's, it's likely to be analog, you know, just like, you know, power, so it can supply power to the thing from the production test jig. They've probably got a huge board. They plug like 100 of these things, maybe, you know, upside down or something perhaps. I don't know, it doesn't matter. Anyway, they plug them in. It might have to be upside down because this header's on the top, so you might have to actually flip it upside down to put it inside the onto the production test board. Anyway, regardless of the physical arrangement, they've probably got like 100 of these, put them on a big tray, and then they maybe put them in a big thermal chamber, and they can then read out and log, no doubt, data from each individual one. So, but this opens the possibility that maybe is there digital compensation on here, perhaps, where they can actually software trim this thing, but that's probably unlikely. I'm getting a bit too excited there because that would be a bit too much, because you don't need to go to that sort of effort for a voltage reference on here. As I've always said, with voltage reference is all about the stability, the absolute accuracy of the voltage reference does not matter. This voltage reference board could be, you know, 1 or 2% accurate. Absolute accurate. It doesn't matter whether it's, you know, 10.1 volts or 10 volts, because when you put it in to the multimeter, you can software calibrate that value out. It's all about the drift. In this case, it's a 16 ppm accurate one, or I think it's 0.5 ppm per degree C temperature drift. I have to double check that. So let's take a brief look at the specs here, because it's very worthwhile. Look at this. Its best spec here is going to be on the 10 volt range here, and like usually like on cheaper meters they might use like a 200 millivolt reference or something like that. So the best DC volts accuracy is going to be on your millivolt range, but this is likely using a 10 volt reference in here, so it's no surprise for finding our best spec here, absolute spec, is on our 10 volt range for DC volts. And of course, for any multimeter, it's the DC voltage range which is going to have the best spec. Current is going to be lower, AC voltage is going to be, well, worse, AC voltage is going to be worse, resistance, current, all that sort of stuff. DC volts is where the business is at, and this is how they get the banner spec of 16 ppm. And you can see where they get their banner spec of 16 ppm here, 0.0016% absolute after 1 year for a plus minus 5 degree differential from the temperature that it was calibrated at. But look at the 24-hour spec here. Look at this, 8 ppm. Woohoo, absolute. Oh, now we're talking. That's the percentage of the reading plus the percentage of the range. You're going to have 2 ppm percentage of the range. When you're down there counting your, counting your least significant digits, that's all going to add up and matter. But anyway, this one is only like a transfer standard spec because it's within plus minus 1 degree C of when it was calibrated. So you usually can't ship the thing within 24 hours and then use it somewhere else. So that's really within the same lab standard. But even something more practical here, look at 90-day spec, it's still 13 ppm absolute. And then that goes up to 16 ppm after a year, 20 ppm after 2 years. So very, very nice. Now here's one of the interesting things, the auto cal feature which we saw on the front panel before. What it does is it compensates, improves the temperature coefficient, the temperature drift of this thing. So without the auto cal feature, i.e. just like the 34471A, for example, then it's going to drift by 5 ppm per degree C of the reading plus 1 ppm of the full scale range as well. And that's basically either, doesn't matter whether it's within this plus minus 5 degrees or outside it, it's just going to always drift by that amount. But you turn auto cal on, bingo, it drops that from 5 ppm down to 1 ppm plus 1 down here, of course, and it's a bit worse down here, probably as you'd expect on the 100 millivolt range there. But yeah, it gives you down to 1 ppm. So you're basically, with the auto cal feature on, you're looking at sort of like a worst case of 2 ppm per degree C temperature drift within the operational range of the instrument. But as with all datasheet values like this from a reputable manufacturer like Keysight, who really know what they're doing and do take care with their stuff, these specs are going to be conservative. So I'm pretty sure it's actually going to be a better temperature coefficient than what you can get here. This is just what is guaranteed. So yeah, it could certainly be better. One thing I really like though is that they do give you a 2-year spec for plus minus 5 degrees. A lot of companies won't give you a 2-year spec on the thing. They'll even give you a year, or some only give you like a 90-day spec. In fact, I think HP used to do that back in the day on some of their meters. They'd only give you a 90-day spec, but they're pretty confident on this sucker, so they're giving you a 2-year spec. Very nice, 20 ppm class instrument after 2 years. Switch on the auto cal, it compensates for the temperature coefficient in that thing, so it must have a good temperature sensor inside this thing. It must be pretty schmick. We might find that on the board there somewhere perhaps. So I'm wondering, is that puppy there a temperature sensor? 3-pin TO92 package? Could very well be. Although it is labelled Q1 there, so Q is for transistor. Aha, it's a bottom entry socket. That's the thing I was talking about before, how they would put these on a big production test panel and they might have to flip it upside down. No, this is a bottom entry socket. So if I just, it wiggles, look at that, I'm wiggling the voltage reference. If I just pull on that, it should just pull up. Yep, there we go, because we've got our pin header on the board and that just fits neatly around that crystal there. They've designed that in, and ta-da, there is our voltage reference. There's not much on there at all, so I suspect that's just like an LTC 1000 voltage reference. Let's take that plastic clip off and see if we're right. And I was right. There you go, LTZ 1000, no surprises whatsoever for finding that in there. The date code on that, the 27th week 2013, so that's a a reasonably old beast. Anyway, it is the LTZ1000 ACH. I'll link it in down below. It's one of the best voltage references you can get. And to get the specs in this thing, it couldn't have used anything else, basically. It couldn't have used your traditional LM399, which we're so used to seeing in, you know, 6.5 digit meters. It's been the standard in 6.5 digit meters for like ever. So, yeah, no surprises. It's still in the new model of the, what is it, the 34465A, as well as the 61A we've seen before. But anyway, we have ourselves a Linear Tech. Probably that's just a op amp, is it? Yeah, a 1013. I think we've just got ourselves an op amp there, and a couple of miscellaneous parts. That's just forming the voltage reference, probably just based on the application note from the LTZ 1000. And that's all she wrote. There's nothing on the bottom here. We've got our holes for our header to come through, so that's quite clever. So as I said, there's a big production test board, no doubt, that individually soaks each one of these, and of course each one is individually serial numbered. There we go, 34470A, specifically designed for this. And in case you're wondering, well, it looks like they had a looks like they had some pads on there, maybe for a bypass cap or something they decided not to fit. Anyway, in case you're wondering what these slots around here are, this big one here and around like that, that is to take the stress off the leads. That's for thermal expansion of the board, of the PCB material. It looks like it's standard, you know, FR4 class fiberglass board. May not be. It may have a lower thermal expansion coefficient perhaps, but that's what they're trying to do there, because any expansion of this board, they're just trying to take out the stress from the leads. That's one technique of doing moons like that. Often you'd like put it on like a cutout right on the edge of the board, for example. Either way, you know, works. I think this one's probably not quite as efficient as the other way, just having like it right on the edge of the board and then cutting a slot out like that. But anyway, it's obviously going to do the business, and that's what it's there for, because any stress on those leads, any mechanical stress on those leads, translates into stress inside the die. I mean, we're really down to the physics level here, and you know, stress on the die in there or whatever, and it can cause the thing to drift. So these things are very, very susceptible. And of course, the reason that they've designed this custom little case is to keep that nice and toasty inside there. Not toasty, but keep it at a constant temperature, so that in your unit like this, because it's got a fan inside it, okay, and there's air blowing through because, hey, we have to cool down the other parts and stuff like that. You don't want that airflow going over your voltage reference down in here. That's just going to ruin your day. So you don't want that turbulent airflow blowing over that thing. So that's why they've done it. They've put it in its own little custom plastic clip, and that one clips on the bottom, and it is all very, very nice and well designed. That's brilliant. Look at that. That one goes over there, and there's a screw to hold it all together. They know what they're doing. Agilent, sorry, Keysight. And there you go, there's the money shot for you Volt Nuts, LTZ 1000 for the win. But, oh, look at that. It's a 2N3904 NPN transistor. Oh, what a letdown. But hey, actually, with hindsight, it's not that surprising, because they need a drive transistor to drive the heater inside this puppy, because this is a heated reference. There's a heating element in there, which I'll show you in a second, hence why they've put it inside here. So that's the idea behind that. So let's take a look at the application note, and they're almost certainly running exactly the same application note as LT are supplying in their datasheet. Let's take a look. So this is what we've got inside the LTZ 1000. We've got a couple of transistors, the buried Xena reference, of course, that's doing all the main magic here, and a heater element showing like this. These are just substrate diodes, they tell you there, so they're just, yeah, not actually a physical diode as such, but that's just clamping as part of the resistive element in there. So that's basically all there is in there, and this puppy is capable of, look, temperature drifts of better than 0.03 ppm per degree C and long-term stability, 1 microvolt per month, and it's about 0.15 ppm noise is also obtained. So that's, you know, the noise figure is basically what Agilent might be, Keysight, might be telling us here with the spec, because it's the reference they're using is capable of better than the spec they've got here. But hey, that's not uncommon for high-end manufacturers like Keysight to overspec their gear. It's sort of like a worst-case guaranteed figure they put in the datasheet. So the reference is certainly capable of better than what they've had here in their reference of 0.1 ppm. It's capable of almost an order of magnitude better than that. And no surprises that the application node here has exactly the same chip. We've got the LTC1013. It's a dual precision reference here. There's our 2N3904, which is driving all of the current for our heater element. That takes a significant amount of current. I'm not sure what it is, but yeah, it's not trivial, hence why they've got the probably the TO92 package there, and also have isolated it outside here, because you don't want that device getting warm inside here. That'd be a big no-no. So you want that out there where the airflow, the main airflow you've designed into your product, can actually take that, you know, that heat away. It can dissipate it. If you put it under there, even, you know, that would have been a bit of a fail. So yes, I have no doubt that this circuit matches this pretty close to precisely, because hey, why would you do it? You know, why would you try and do it against what linear technology, one of the masters in the field, has spent a lot of time and effort building one of the world's best voltage references here, and getting and characterizing a circuit? Well, you just use it and go, yep. Of course, you do your own tests and performance checks on it. I'm sure Keysight have done that. They're not just going to blindly build this up and go, yeah, she'll be right, no worries, whack it in there and off to market we go. No, they would have seriously characterized the design of this thing, and as I said, they've really thought about it from a thermal airflow point of view, and thermal stress on the board and everything. They've really done it right. That's a brilliant example of how to design a nice precision reference. So it'd be interesting to know exactly what burn-in they do on these, because I'm sure that they do. So, and of course there's no trimmers on here. As I said, they're not worried about trimming this to an absolute value. It doesn't matter, because that's taken care of in the software calibration of the meter itself. So that capability is already built into the multimeter. There's no point trying to get an absolute reference here. So this could be a couple of % off. Doesn't matter. It's all about the drift. It'd be interesting to know, and maybe Keysight can get back to us about what sort of production testing, maybe if they've even got some photos they can share of their production test facility for these things or something like that. I'm sure they whack them in a thermal chamber and characterize each one. Bet your bottom dollar. Okay, so I won't bore you with any more details of the teardown in here, because I've done it all before in the 34460A video, which I'll link in down below, and I've done like little Dave Cat explanations of how their multi-slope converter works and all that sort of stuff. So there's some real interesting info in the previous teardown, because it's an identical design basically, and you'll see in a second. I've taken some high-res photos of both of these boards as aligned as I possibly can, and well, let's go to the videotape. Alright, here we go. Let's compare the two boards, and this is the original one. This is the 34461A. You can see the Agilent logo up in the top right corner here, and you can see that here's the part number 34460A, which is 60/61, and it's a Rev 4 board. Now, look at this. I can switch between them. Isn't that fantastic? I love it. Oh man, I could play with this all day long. Look at this. You can see that there's hardly any differences at all. It's terrific. But anyway, here's the new Keysight one. This is the 34465. So the same PCB is shared between the 65 model and the 70, which we're tearing down here. Once again, Rev 04 again, if you have a look at that. So you'll notice that one of the first things you notice is that, well, the relays have changed to yellow. Woohoo, excellent. They've changed brands. They've gone from Omron. But look, there's a missing relay on the old 660 board, I'll call it, and the relay is populated, and also there's another relay here and two SO8 packages here as well, and you'll see that they just pop in there, and so maybe they had the design of they were thinking about this right back when they designed the 6.0 and 6.1. So it looks like they've had the capability in there, but a few minor things have changed. Look, the Keysight one up here where the cursor is, they've added a couple of parts up there, so they've squeezed them in there, and they've changed the layout of this. You see how on the old one they've got the large footprint for that oscillator there, but then they decided, well, no, we're going on this smaller package, and they've changed it, and they've sort of just shuffled a few parts around there, around the analog to digital converter section around here, which is based on the lattice part. The lattice part is the exactly the same device. It's the LFXP2-5E. But you'll notice that, look, there's a part that's, oh no, a resistor. They've moved that, but I think something else is added in there. No, anyway, there's minor differences in the tracking and things like that, but geez, there's not much at all difference. Check out this down here in the bottom left corner. Look, this R102 here is, oh no, it's mounted upside down. All the electrons are going to fall out. Oops. But it's, gee, look, everything's pretty identical. It's got all the same input protection. They still don't have that second MOV fitted there. And this precision resistor R416 is still here. These two ceramic packages here and here are still the same. All the analog to digital converter is all still the same. They're just trying to squeeze out some extra resolution from it, of course, which they can, because the meters always had that extra resolution in there. If you see my review last time, it actually does a software calculation, gives a single precision floating point output value, which is like equivalent to like 8.5 digits or something like that. It's more than the quoted 6.5 digits that was on the previous unit. So it was obviously good enough for this 7.5 digit meter. And you'll notice, here we go, here's the change, here's the voltage reference, the LM399 in there, and you'll notice that they've basically just ripped out the LM399, even that, look, even that capacitor in there and that diode in that SOT23 package there, they've basically just ripped out the LM399 and replaced it with the LTZ1000. So there you go. Oh, look, there's an extra resistor there. Look, R310. Maybe, I don't know, is that a current shunt for the 1 microamp range? That's the other thing I haven't found, how they're doing the 1 microamp range, because that's 2 orders of magnitude better than the 6.0 model here, which only went down to 100 microamps full-scale range. So this one can do 1 microamp. How's it doing it? I don't know. Everything looks identical on the bottom side of the board. All the current shunts look the same there. So I'm not sure what... Can anyone spot it? Can anyone spot it? I don't know. Anyway, we've got our high voltage resistor hybrid over here. They've got a high voltage network here. And everything looks pretty identical. So, oh, here we go. No, sorry. They've... No, look, here we go. Well, they've changed the type of current shunt resistor used here. Look, R231 here. You see how it's like, that's very similar to one I use in my microcurrent, a very similar sort of design. But look, they've changed that to a much larger package now. It's only a 1% value, but as I said, it doesn't need to be precise because it's software calibrated out. It'll be incredibly low drift. And that's a weird-ass 4-pin package. You'll notice, like surface mount. It's still a surface mount package, but it's much bigger, physically much bigger, so it has a greater power dissipation in it, but it's still a 4-terminal current shunt resistor in there. So maybe they've changed that, and maybe are amplifying. Maybe those two there are an amplifier, perhaps, with, you know, that boosts it up. I'm going to have to have a look. Oh, iBoot. What does that mean? Current boot. Interesting. Aha, yes, my hunch was correct. These devices here that they've added, 2 extra devices here, you'll notice, can I zoom in on that? No, I can't. But you'll notice that there's a guard ring around that trace there, and whenever you see guard rings around there, sorry about the small cursor here, I probably should change to a really large cursor so that you can see it. But when you see guard ring like that, you know it's a sensitive node. So we're talking, you know, low current stuff into there. So bingo, this chip, you probably can't read it there, but it is none other than a analog devices AD8638. Bingo, exactly what you need for, like, it's like my microcurrent capability. It's got an auto 0 rail to rail op amp in it, i.e. it's got 0 DC offset in it. There's 0 offset voltage, and that's exactly what you need for measuring down at that sort of, you know, that low end. This is how I'm sure that they're getting their 1 microamp range, and they've got 2 of those in there actually. If we go back here, we'll see this one here is still fitted. That one is still one of those devices, but they've fitted another one in here. U202 there. I think U203 is just a TL071. It's just a Joe Blogs op amp. Nothing fancy going on there at all. But yeah, I actually looked at using this in my microcurrent at one stage, I think. And this one's a pretty schmick op amp in very low input bias current, 40 puff. And what's the typical low offset voltage? 9 microvolts maximum. So it's actually not as good as my microcurrent, but that doesn't necessarily matter. It's going to be because, once again, they can calibrate that out. So it's the offset drift here which is going to matter. So it's 0.04 microvolts per degree C maximum. So that's how they're probably getting using this device to get their 1 microamp full scale range, and they can still get presumably there's 7.5 digit precision on that. But if you actually went back and checked the spec, the drift spec would actually be higher for the current ranges. And there's just other little tiny changes here. You'll notice just under the lattice chip here, you'll notice how they've just changed the, just rotated that component designator R808 there. So the PCB designer was just fussing around. Oh, I think I'd rather have it in that orientation. That's a bit neater. They were just, you know, gilding the lily there a bit. And like down here around this, the 94V0, they've added a dash in there for some reason. Who knows? And but like apart from this, like there's bugger all different. So I'm really surprised. And the other noticeable difference here is what looks like a crystal there, but it's not actually. Sorry, I've only got the top-down photo here, but it's actually a Vishay Z-foil precision resistor. So it's a 10K precision resistor. This one was not fitted. As you can see, it was not fitted on the original 6061, but it is fitted, so it's R324 there, but it's, yeah, a really precision 10K resistor. So why they've added that in, perhaps it has something to do with the current shunts, but it seems like, yeah, it's just out of the way, tucked over there. So I'm not sure why they've put the extra one in there. Anyway, it is a very schmick resistor, so very extremely low Temco. It's one of Vishay's best ones. It's the VH102ZT. You'll notice that, look here, they've changed manufacturer of that. What is it? What is it? A 74? It's a HC4053 analog mux. You'll notice that they've changed manufacturers from TI to somewhere else. I haven't zoomed in on that one. Can't see detail, but obviously they're for like they are not critical parts. They're just, you know, jelly bean parts. So really, you know, it doesn't matter what manufacturer you put in there pretty much, although they would have characterized it, specified it, and put it in their bill of materials as that is an authorized, you know, replacement part. So, you know, a company with the reputation of Agilent, they wouldn't just get whatever they can get from the Shenzhen market this week. It doesn't work like that in these kind of things. But you'll notice that with that amplifier over there, I still don't know what that iBoot is. So yeah, I don't know what that means. It's been removed here, I think. on the new unit, so that's rather interesting, and they've added that extra resistor there as well. So they certainly have changed the current range configuration, because they've got two additional current ranges, the 10 microamp and the 1 microamp, so you expect a few changes around there, but yeah, it's basically identical. Very, very interesting. So they haven't added a huge amount in here for the price difference. What they're basically, you know, they've got a couple of extra op amps in here. Okay, fine and dandy, but you're basically paying for the LTZ 1000 reference and the characterization of that reference. As I said, they probably go to a lot of effort to, you know, individually thermal chamber test each one of those, etc. So yeah, and here's another interesting thing. Look, you'll notice just around that chip there that has a thermal pad on the bottom. That's why it's that gold color. It's got exposed copper there. They're using that as a little heatsink. It's got some solder. It looks like they had excess solder paste, or it's flowed through the vias from the bottom or something. So they maybe changed their paste. Well, they had to have changed their paste stencil, because there are a few differences in the layout. So instantly have to go to a new solder paste stencil, but maybe they've applied some extra paste on there and it's just flowed out. Anyway, just an interesting little insight there. But yep, everything looks pretty much damn well identical. I love it. All the value is in the voltage reference. And if we have a look at the bottom of the board, I won't do the same high-res photo thing here. Once again, teardown photos are on EEVblog.com if you want to have a look. This is, actually I've lost track. This is the old one, the 61A, and this is the new 67A. Basically identical, except, look, I can actually see this one actually has an extra resistor populated in there, where this one doesn't, but yeah, there might be a few little miscellaneous differences, but basically the big current shunt resistor up there is exactly the same from Dale. Yep, it's basically identical. So there you go. I hope you enjoyed that teardown of the new Keysight 34470A. So thanks for Keysight for getting this to me. It was a bit late. I was hoping to get this before it was released, but yeah, there was a few shipment delay problems. But thank you very much, Agilent. Very, very interesting and absolutely brilliant first-class quality bench multimeter. It's almost impossible to fault this thing, really. Fantastic. So, hope you enjoyed that. If you did, please give it a big thumbs up. And as always, if you want to discuss it, jump on over to the EEVblog forum, link down below, or leave YouTube comments or blog comments. Catch you next time. The longer your capacitor takes to charge up, the greater your resolution. But, therefore, you're trading off measurement resolution versus speed. But a modern high-end bench multimeter like this Agilent, or even the previous model, or the previous model before that, or before that, they don't use just basic run-of-the-mill dual-slope integration techniques. They use what's called multi-slope integrating ADC, and it works exactly the same way. It's just that it has some extra switching in here.